Not yet.
Welcome everybody to the last reading Groupoid of this year 2025. And today we have the pleasure to have a speaker, Óscar Carballal, who shall talk about constructions and equivalences in the category of Lie groupoids. Please, Óscar, the cyber floor is all yours.
Thank you, Sir, for the introduction. So yeah, as Sir said, I'm going to talk about some constructions and a very precise notion of equivalence in the category of Lie groupoids, right? Well, therefore, in this part, I will not follow Mackenzie's book, but some papers by Burstein, Matías Del Hoyo, and also the book by Morita and Marson, right? So first of all, I will start like recalling what is the precise notion of a good pullback in the category of manifolds, right? And why the usual pullback as topological spaces does not work in the smooth manifolds category. Then I shall introduce the notion of pullback of a groupoid along a smooth map. And then I will also show what is the notion of fiber products of groupoids in the sense of Burstein, Del Hoyo and Cabrera, which is indeed a very more general notion when compared to that appearing in Mackenzie's book. Finally, I will talk about homotopy pullbacks, right? Which is a very, well, it's a bit technical, but important notion in order to talk about what a Morita map between groupoids is. And then therefore we shall say what is the very precise notion of a differentiable stack, right? So first of all, the first section is that of good pullbacks of manifolds, right? Good pullbacks of manifolds. Well, so first of all, let us consider the following example, right? Well, consider these two smooth maps, right? F and G, which are defined from R to R2. This is the R curves, right? F is just a line, and GDT is this, right? Okay, so the image of these two smooth maps, right, are the following ones. This is the y-axis, this is the x-axis, and we have like ft is this one here, right? This f, and our g is like, you know, like this 3-degree polynomial, right? And this is g, right? And the point is like whenever we consider this diagram of the smooth manifolds, of maps of the smooth manifolds, this G, this is F, and this is just the inclusion, right? The arrow from 0. This diagram is a pullback, right? As topological spaces, in the sense that precisely we can say that this thing here has the universal property of the pullback and so on, and it is canonically isomorphic to this set where the arrow G and the arrow F are equal, right? And this is because, you know, if we have that ft equals to gt, this is somehow the intersection point of these two curves is only the origin, right? This point here. And precisely this is a pullback, right? Okay, but the point is that when we apply the tangent factor to this pullback here, at the point 0, the resulting diagram, which is this one, Here I take the tangent map of G at 0 and the tangent map of F at 0. This diagram is not a pullback, right? So this means that, well, precisely if you want the pullback of these two things here, right, over these maps, if you want with this notation, I mean, this is canonically isomorphic to the vector space said that U equals V, and this is, of course, right? So the thing is like, well, in the category of smooth manifolds, you may have like a pullback of manifolds as topological spaces with the universal property in the topological spaces category, but it is not longer a pullback when we consider the tangent factor, right? So somehow we have to introduce another notion of pullbacks in the category of smooth manifolds. And this is following Matías del Hoyo, what we say is a good pullback of manifolds. Let me recall it. So this is definition. A pullback of smooth manifolds is, something like this. This is two manifolds N1 and 2. Here I have N1. And then I have these two maps. Let's say F2, F1 to M. And I take the pullback over M, right? F1 and F2 are just smooth maps of manifolds. And we say precisely that this pullback is a good pullback if the following two conditions are satisfied. The first one is that it is a pullback, right, in the category of topological spaces. In this category, right, in the category of topological spaces. And the second one is like the expected tangent space of this pullback, right? The one here behaves as one should want, right? And I'm precisely saying that this for every x1, x2, such that we have this thing here. We have that following a sequence of vector spaces. Here is just the inclusion, right? And the crucial point is this arrow here. Let me write it in red, which is the tangent map of F1 at x1 minus the tangent 1, the tangent 2. And here we have like the tangent space at x, right? In M. So the fact that this sequence of vector spaces is exact precisely means that the tangent space at a point x1, x2 in this pullback is precisely the one should expect like coming from a pullback, right? Well, and indeed, we can also say that, that this is equivalent to the following. Well, the first thing is that as one should want, this thing here is a closed embedding And of course, we have like the expected tangent spaces. Okay. So, well, in general, to check this condition, I mean, it is not difficult, but the general criterion, as probably you all expect, is to have transversality, right? That if F1 is transversal to F2, then the pullback of manifolds exists. And moreover, it is a good pullback in the sense that not only the first condition of being a pullback in the category of topological spaces holds, but we also have like the expected tangent spaces, which is somehow the important thing for us also. Right? And as you probably know from a basic differential topology course, here we know that a submersion, subjective submersion, submersion is always transverse to any other map. So somehow like the important thing is if you have transversality, you're in a good place. And if moreover one of the maps to form the pullback is a submersion, then everything holds very great. So now let us go to groupoids, which is also the interesting thing for us. And let us define what is the notion of pullback groupoid along a map, right? Which is the second section. And I will present something which is more general than Mackenzie's construction. You can find this construction in the book like by Murdick and Marson, right? I will tell you like at the end of the talk, the precise part. Okay. So the context in which we will work is the following one. Well, first of all, let us consider a groupoid over a manifold M, right? And a smooth map from another manifold onto M, right? And we define the following set of, well, it will be the set of arrows, but in Mackenzie's notation is this things here, which is this fiber product with the notation of the maps is like FT. Here we have G, sorry, and here we have S and right, F, right, and prime. Yeah. And this is precisely the set consisting of points Y, G, X prime, which belongs to M prime, groupoid, M prime, such that if you want, we can write this thing here as the image of Y prime and X prime are points of M, and G is a groupoid over M. We consider that those arrows which precisely join the images between X prime and this thing here, right? If you well, so in general, we will define a set groupoid structure here, not necessarily a Lie groupoid one, and we will like obtain some conditions for this structure to be precisely smooth and set consequently into the Lie groupoid category. Okay, so of course we want to have a Lie groupoid here over M prime. And we have to define the source and the target maps, right? Well, of course, if we have like this arrow, this source will be like the point in M, which is X prime. The target will be y prime, and it's like the partially defined multiplication on composable arrows, which is something like this. It's just composing on appropriately on the original groupoid. This thing here, right? And the unit of every point x prime belonging to n prime is just like the identity arrow on the image of x prime. This thing, right? This thing here, right? Okay, so in general, this is only the structure of a set groupoid, right? It's always, well, for sure, n prime is always a manifold, but this thing here, right, which is a somehow double pullback, is in general not a manifold. So we have like obtained some conditions from our maps in order to define a smooth structure here, right? And for sure, we will construct it using good pullbacks, right? Okay. So, well, first of all, is that this thing here, as you see, we have like two pullbacks, right? And this is precisely saying that the following diagram is commutative, right? Well, I will work it in a different page because it's somehow big. Okay. Wait a minute because this is a bit long. This is projection onto the first factor, G. This is, well, the target of G, and this is M. Oh, sorry. This is source. It is M prime. Wait, sorry. This one has to be a bit shorter. Okay. And this is F. This source target. Okay, this is just the projection. And this is our smooth map, right? So, I mean, saying that from our construction of this thing here, we have the following diagram of pullbacks, right? So we have like a lower pullback, which is this thing here. Well, no, the lower pullback is this one, right? And this is very easy. And the point is like, after analyzing this one, we have to analyze the other one, which is like this one here, the upper pullback, and to obtain conditions in order this thing here to be a pullback and a smooth manifold, right? Okay, so first of all, just let me recall that this thing here, right, which in Mackenzie notation, if you want, is like the G x prime, such that the source of G equals to F x prime, right? And this diagram here is always a good pullback, right? Why? Because here, in one of the arrows, we have like the source target map of the Lie groupoid G, which is always a surjective submersion, right? And consequently, it's always transferred to this thing here. So the first observation is like, it's a good pullback, right? Because like the source map of G is a surjective summation. Okay, so now the natural thing will say, okay, in order to study like this upper pullback here, well, upper pullback, no, upper diagram to be a pullback, one maybe should require like F being a surjective summation. Okay, this, I mean, if F is a surjective summation, for sure it works. And is moreover like the usual case in practice, but one could say a more interesting thing for our purposes, which is precisely requiring that surjective submersion is this arrow here, right? The composition of T with the projection. And as we will say when talking about Morita maps, this is a very natural condition, even more natural than requiring that F is a surjective submersion. So provided that we have that this composition here is a surjective submersion, then what we know is that our thing here is indeed a smooth manifold, and this diagram is a good pullback. And by our construction, it's like we can compose these two diagrams here, and it's not difficult to see that these two conditions precisely implies that we have another good pullback diagram, which is the following one. This map here is the anchor of our new Lie groupoid over M prime. And this diagram is a pullback. Right? This is a very natural thing when talking about Morita maps. We will see later. But the point here is like, well, what Mackenzie does is like, he requires these two maps to be transversal, okay? In order to define this structure, this smooth structure here. And what we have seen is like, considering a double pullback, we can skip the condition about this map being transversal to the anchor here, right? So our construction is more general than Mackenzie. Well, our construction is like in the construction coming from Merdick and Marson, but yeah, I mean, it is more general than what Mackenzie does. And the interesting thing here is like this groupoid here, under these conditions, let me write it in this way, is the pullback groupoid. Of our original groupoid, which is over M, but along the map. And also interesting thing here by construction is that, well, recall that this thing here, the set of arrows, is just arrows from the image of X prime to the image of Y prime, right? So this thing here has a natural projection, right, onto G, which is like, if we have arrow G connecting the image of X prime and Y prime, then the projection is just this thing here. And the fact is like this natural projection, right, together with the map F from M prime to M is a morphism of Lie groupoids. And indeed, this is a very easy consequence because of the definition of our pullback groupoid here, right? Because we are just saying that this is arrows connecting images of points, and this is precisely somehow the condition of being a morphism of Lie groupoids. Right. So now let me introduce the following example, which I think that is somehow very illustrative for our purposes. So do you have any doubt or comment so far?
Maybe a quick question, Oscar. This
Sure.
pullback of the Lie groupoid can be considered as a pullback in the Lie groupoid category?
With a universal property, you mean?
Yes.
Well, I think that the answer is no. I mean, this is because somehow, I mean, it satisfies like the universal property for the pullback of manifolds, that is clear, but for Lie groupoids category, you need to take the pullback of two Lie groupoids. So the precise notion of that is that of fiber product we will talk later on about that, but maybe in this case, I don't know, I have to think about it, but maybe if we consider the M prime manifold as a Lie groupoid over itself, maybe it is, I am not sure, Ruben. I mean, we can check it later when talking about fiber products if the two notions coincide in this case. I think yes, but I don't know. Well, so the interesting thing for us now is the following example. Well, because it is true that when we have this pullback groupoid, somehow we can also factorize I don't know. I have to think about it. But now the following example, right, which is for pullback groupoids and is about foliation, right? So let alpha be an irrational number. Okay, and let us take this vector field on R2 with global coordinates x and y. Right, and let us take one of our favorite manifolds, which is the two-dimensional tori. And we have the universal covering projection, this thing here. Two-dimensional torus, if you want, is the product of two circles, right? And we take the push forward of this vector field, right? It can be proved that this thing here, right? Sorry. When we take this thing here, this defines the constant rank of rank 1 for sure. Vector subbundle of the tangent bundle of the torus. This means precisely that it is an integrable Frobenius distribution, if you want in the usual sense, that is regular of constant rank, and therefore it induces a foliation, right? By Frobenius theorem. On the torus, right? This foliation is called the Kronecker foliation. Well, and the point here is well, let me draw a picture. Well, I will try. No, not in this way. But this thing here, we have our torus, right? And precisely the integral, the leaves of this foliation corresponds precisely to the integral curves of our projected vector field. And maybe you are familiar with this foliation because it is one familiar example. It is this thing here. Well, I tried. No, this thing here, right? And the point is since our parameter alpha is an irrational number, every leaf is diffeomorphic to the real line, right? But the point is every leaf is dense in the torus. Well, what this implies is, for instance, that when we take the leaf, when we consider this is, yeah, it is, okay, yeah. The associated leaf space, right, which is this quotient here, is a non-Hausdorff manifold. Okay. Well, this is only with one S, sorry. Okay, so now we will study this foliation using Lie groupoids, right? And this quotient here is not only non-Hausdorff, it possesses non-orbifold structure. And the induced quotient topology is like the trivial topology, which is for sure very bad. But as you can imagine, this foliation is indeed very interesting. And Lie groupoids provide a way to study these things, right? Which from my point of view is like, it's pretty well established, it's pretty formal, things are very clear when you consider groupoids. So that's our main motivation, right? Okay, so now, well, let me recall that I think we have not talked about this groupoid yet, but it's indeed a very natural one. Well, associated with every foliation on a manifold M, we can define the associated monodromy groupoid of the foliation. For sure, these concepts here are for like constant rank foliation, not for singular foliation. For singular foliations, I mean, the whole theory is like more different. One has to do different constructions, but I am aware that some things, I mean, very interesting things have been done there. But just for now, the foliation is of constant rank, right? Well, so the associated monodromy groupoid is the following Lie groupoid. It is denoted in this way, right? And the set of arrows precisely consists on homotopy classes joining 2 points y and x, which are on the same leaf of the foliation. And if 2 points are in different leaves, the set of arrows joining them is the empty set, right? So the arrows consist only on homotopy classes relative to 2 points living in the same leaf, right? And this is in a very natural way, for sure, is like you only consider like the source is like the starting point of the homotopy class, and it's like the target of an arrow is like the end point of the path lying in the homotopy class. And this, I mean, one can prove like it's not easy for sure, but I mean, to prove that this thing here has one can prove that this thing here has a smooth manifold structure. And very interesting, if you consider like the isotopic group of this monodromy groupoid at a point X, this consists precisely on paths which join precisely X, which start on X and end on X, and they are homotopy classes, right? So this is just the fundamental group of the leaf containing the point X, right, relative to that point. And I mean, we can omit the point since we are assuming that it is collective, right? Okay. So now the question is, what is the precise, can we describe in some way the monodromy groupoid of the Kronecker foliation in the two-dimensional torus? And the answer is yes. But it is not an easy result, but we can somehow like say precisely what this groupoid is, right? So for F, dichronica foliation, dichronica, sorry. On the torus, like somehow you have to use this thing here. That the two-dimensional torus, well, sorry, this way. The two-dimensional torus is like the product of two circles. We can precisely obtain that the monotomy groupoid can be is this thing here, right? Sorry. And well, to check this formula, I mean, I will refer to the book of Marson and Mordic when they compute like this kind of identities for a very general class of monodromy groupoids and also for holonomy groupoids. And the thing here somehow in order to explain this formula is like what we have here, what is just the universal covering space of the two-dimensional torus, right? And here somehow what we have is an S1, which is wow, how to explain? It's like another manifold which is also equipped with a left set action, and well, what Mordic and Marson do in their book is like they obtain a way to describe like these monodromy groupoids using universal coverings and so on in a very precise way. And they indeed find that the monodromy groupoid can be described in this way. But this is not important for our purposes, right? Okay, so we are interested to relating this thing with pullbacks, right? Okay, so now we will consider what is called a complete transversal section of the foliation, right? A complete transversal section, right, of a foliation is just, well, transversal is saying that somehow it's a manifold, a submanifold of M with a very proper topology, such that it is transversal to every leaf somehow, right? So the dimension of our submanifold S has to be like the codimension of the foliation. Well, the complete transversal section, sorry. Okay, so the precise definition of this is just a submanifold of M intersecting every leaf non-trivially in at least one point for every leaf. And such that the dimension of S equals to the codimension of the foliation, right? So imagine that, for instance, you have like a foliation consisting of planes on R3. This is the foliation, and a completely transversal submanifold in this case is like some curve here, right? It is this thing. And you can like imagine more complicated things like, I don't know, something like this. Also holds, right? Well, so in our case, in order to take a completely transversal section of our, this is in general, but we are working on the two-dimensional torus with the chronicle foliation. Remember that in our case, we have like the two-dimensional torus here. We have like this is, well, this is the canonical foliation. And in order to take a completely transversal submanifold, we can take like something here in this way, which is like, remember that we have like the torus is like the product of two circles. So we can take S, like being, for instance, one of the angles constants, where here we have like this is theta phi, right? And this is completely transversal to the canonical foliation. Okay, and for sure this thing here is like, so to take a completely transversal section of the canonical foliation, take just one of the S1 copies lying on the two-dimensional torus. And in this case, what we have is like our technical condition for the pullback groupoid to exist holds, right? It can be proved that in this case, this thing here, which is defined, sorry, I'm writing M all the time. And this is a surjective submersion, right? Indeed, it can be proved that it is a surjective local diffeomorphism, but for sure is submersion, which is the important thing. And provided that this holds by our following result, what we have is like this pullback groupoid here is a Lie groupoid over our S, which is our completely transversal section of our foliation. But the important thing here is like the dimension of the manifold of arrows, this thing here, well, in this case, somehow the set of arrow here just refers like to the homotopy classes on a same leaf of the canonical foliation starting and ending on points of S, right? Well, and in this case, because in this case of dimensions, it can be checked very easily that this has dimension 1. And S for sure has dimension 1. So this is a Lie groupoid over the base such that the manifold of arrows has the same dimension as the manifold of objects. A Lie groupoid with this property of dimensions is called is an étal groupoid. Right? This is a Lie groupoid such that the dimension of the manifold of arrows equals to the dimension of the manifold of objects. Well, and what we have done here, just for simplicity, with a very particular foliation, the canonical foliation, and a very concrete transversal section holds in general, right? You can check this in the book by Merdick and Marsum, that the general result is like whenever we have a foliation on a manifold and we consider its monodromy groupoid, then let S be an arbitrary complete transversal section of our foliation and construct the pullback of our monodromy groupoid related to that foliation relative to this complete transversal section. Then the resulting groupoid, right, which is a Lie groupoid over the complete transversal section, will always be an étal Lie groupoid, right? This is, as I said, a Lie groupoid such as the dimension of the manifold of arrows equals to the dimension of the base, right? Which in general, this does not hold for the monodromy groupoid, even in our case, for the monodromy groupoid of the canonical foliation, which has dimension 3, right? I mean, this can be checked like using Lie algebras, but it is not the easiest way right now. Okay, so do you have any question, comment so far? Okay. I think that, yep. Okay. I think that the example is very interesting and somehow it is not that difficult and it is nice for me like to see a very concrete foliation. Well, so now the third part is like what is relating to previous comment of Ruben. What is the very precise notion of pullback in the category of Lie groupoids, like fulfilling a universal property? Well, what Mackenzie does in his book is like he considers a very concrete case, what he calls vibration. But here we will introduce another more general concept, which comes indeed from a paper of Enrique Burstein, Matías Del Hoyo, and Alejandro Cabrera. And it's more general than Mackenzie's concept. This is the fiber product of Lie groupoids. Okay, so as one can expect, in order to construct fiber products on any category, like take two morphism and then what is the fiber product concept, right? So let if this two morphism of Lie groupoids onto a same Lie groupoid G over M, right? So this is for E1 and 2, right? So suppose that the maps between the arrows, right? Recall that this being a morphism of Lie groupoids consists of two maps, one map between the manifolds of arrows and another map between the objects, right? So suppose that the maps between the manifolds of arrows, the ones with capital F, induce a good pullback. And remember that this is precisely saying, take the pullback over G, oh, sorry, this is G2, G2, G1, F1, F2, G, right? We have this pullback here also with the property for the exact sequence of tangent spaces. And if the map between the sets of arrows induce a good pullback, and this is a morphism of Lie groupoids, what we have is like the map between the objects also induce a good pullback. Okay, so the good pullback property is somehow only necessary to check it, like for the maps between the sets of arrows. Okay, right. So suppose that we have a morphism of two Lie groupoids onto a same Lie groupoid, right? Such that the morphism between the set of arrows induce a good pullback, right? So that is that F1, F2, and also the match between objects both induce good pullbacks. Then we can construct the notion of fiber product of Lie groupoids, and it behaves very well in the sense that we can take for sure the pullback of the set of arrows, which is this thing here. We know that it exists because F1 and F2 induce a good pullback, the capital Fs. And the point is like, in a very natural way, it is a Lie groupoid over the pullback of the sets of objects, right? So this is a Lie groupoid, provided that both capital Fs and small f's are induce good pullbacks. But the important thing is that not only this thing here, but that this thing here is an embed Lie subgroupoid of this groupoid over the product of the bases. Right? And it satisfies the universal property. So this notion here of fiber products is in this the very precise notion of pullbacks or fiber products, whatever you want, in the category of Lie groupoids, right? So, Ruben, I don't know if this answers your question. Do you think like our previous concept of pullback over along a map fits in this formalism?
I think
I think
what you have said before, right? Like you have to consider the trivial Lie
Yeah.
groupoid structure. I think that makes sense. And then
yeah, I think so. I think so. That whenever in the previous case, like we consider like for the other manifold M prime, the trivial groupoid structure, then that notion of pullback holds fits into this one, right?
I think so.
Yeah, and it satisfies universal property. So yeah.
Yeah.
Okay. So I hope this is clear. This is well, I will send you the references when finishing the talk. But if you want to check this thing, this construction, it is in a paper in Advances in Mathematics by Burstein, Cabrera, and Deloyo. So I mean, the construction is great. I mean, it is not that hard. It is in the appendix of the paper, right? But I mean, it is a lot more general than previous constructions by Mackenzie and also by Mordic and Marson, right? So it is, as far as I know, the most general construction for fiber products, pullbacks of groupoids. Okay. So now, after this construction, which is somehow it is not that difficult, now is the point of the talk where the abstract nonsense enters, right? So I will talk about homotopy pullbacks. And this, in the sense of Mordic and Marson, are also called like weak equivalences of Lie groupoids. So let us start as follows. Let us consider a Lie groupoid G over M, right? And we consider its groupoid of arrows, which is defined as follow. Is the following groupoid. Is denoted by GI, and this is just the set of free composable arrows. And it's a Lie groupoid over the set of arrows. So the objects are now arrows of the previous groupoid, right? And the arrows are commutative squares over arrows of G. So, well, suppose that we have like, better in black, an arrow from X to Y, this thing here, right? And we have another arrow from X prime to Y prime, right? Well, what a commutative diagram, we have arrow here, something here, and something here. Let us call this arrow G prime, this arrow H, and this is H prime. This thing, we have this, and this is G composed with the inverse of H. Okay, so arrows can be identified like using this commutative diagram, right? As triples of free composable arrows, which are just precise. This left arrow here, the arrow connecting X and Y, X prime and Y, sorry, which is like H. And this is a free composable arrow because like the target of, what is this? The target of this is just the source of X, of H, and the target of H is the source of this one. You can check it from the diagram. So it's like joining diagrams. It is a very interesting. Well, yesterday I was like computing everything for this Lie groupoid, like what is the source map, what is the target map, what is the multiplication, what is the inverse. It is not difficult, but it's somehow nice if you like playing with commutative diagrams, right? So what is the source map?
Just a clarification, Oscar. This would be a morphism between G and G prime.
Sorry. What? Sorry.
This commutative diagram. What?
No,
would this?
This commutative diagram. You say like a morphism between G and G prime.
Yeah. I mean,
I think so. Yes. It is.
Okay.
I think it's it. Yeah. I mean, it is the same thing like when in category theory somehow you take like the category with objects morphisms and arrows like natural transformations. Well, not natural transformation. Yeah, but no, the category with objects functors and arrows natural transformations is something like that, right?
Okay. Thanks.
So the source here, you have like the source, the target maps. So whenever we have an arrow here, which is something like this, G prime H minus 1, H minus 1G. To obtain the source, we have like to multiply these two arguments here. And we obtain like with the multiplication of the original groupoid G, and this is just G. The original arrow, right? And to get like the arrow G prime, you consider this commutative diagram. And this is G prime inverse of H, which is G prime, right? And the identity for every arrow G, this is just the commutative diagram with this induced by these things here, right? Okay, and okay. So, well, to define multiplication, it is not difficult. It's like whenever we have like two commutative diagrams which can be composed, I mean that they share somehow the one horizontal line. To obtain like the multiplication of commutative diagrams, we have just like to compose between vertical arrows and there is like one morphism connecting the other two. I mean, it is not difficult. You can check it, but for our purposes, what is important is to know that this the source map here, the target maps, and the unit maps are morphisms of Lie groupoids. Right? Okay. So this is important to define the homotopy pullback, right? It can be done without this, with the groupoid of arrows, but for me it's like using the groupoid of arrows and pullbacks is more natural, right? So now, in general, let us consider two Lie groupoids and two morphisms. As for the case of fiber products, right? Have two Lie groupoids morphisms here over a Lie groupoid G over N, right? Morphisms of Lie groupoids. Well, as we said before, if F1 and if the capital Fs induce good pullbacks, the small f's also induce good pullbacks, right? Okay. So now let us suppose we have now to suppose somehow a stronger thing, which is transversality, right? Suppose now transversality, right? That the capital F is transversal to the another F, and then we have, provided that we have this transversality condition, we have this thing, we can consider this pullback here, which is known as the homotopy pullback. I will explain in a minute. It's just the pullback of the anchor of the groupoid of arrows and the product of F1 and F2, right? And this is the anchor of the groupoid of arrows right here. This thing here is the anchor of the groupoid of arrows. And here we have like G1. Here we have like G times G, right? Okay, and here we have like. So provided that we have like this transversality condition between the maps between arrows and objects, the following diagram is a pullback, right? And this thing here, the pullback of the anchor of the groupoid of arrows and the product of the maps between arrows is what is called the homotopy pullback. Well, okay. So if you want to have a very concrete description of this homotopy pullback, it's like the objects of the homotopy pullback are precisely like triples of this way. A point x1 belonging to m1, a point x2 belonging to m2, and then an arrow of G joining the image via F1 and X2. Something in this way, right? Because remember that F1, X1, F2, X2 both belong to M, and G is here as something here, which is a Lie groupoid over M, right? So this makes sense. The objects are triples of this way. So what are now the arrows? Okay, this is the very, well, it is not abstract nonsense at all, but it is a bit, the notation is like lot of things. So the arrows of this homotopy pullback are triples K1, K2, K3, of the following way. Well, first K1 is just an arrow which is like from X1 to Y1, right? This is MM1, this is, okay. So now we have like, this is K1. So K3 in a similar vein is like an arrow from a point of X2 of M2 to another point, right? Okay, and what is K3? So now what we do is like, we take the images between these two arrows, right? Using the morphism of groupoids we had before. And so what we have here is like the image of Y1, because this is in points, we take like the small f. Suppose we have an arrow here, and we do the same like for the x's. Okay, since K1 was an arrow from X1 to Y1, here the arrow we have is like the image through capital F of K1, sorry. And here we have, and this is with one, F2 and the image of the another arrow, right? Here, suppose that we have like arrows G and H connecting this, and precisely K2 is the arrow here connecting the image of Y2 and the image of here's 2. and the image of x1. Okay, similarly to the groupoid of arrows definition, but well, a bit more difficult with k, which is here, and the arrows are three things in this way. So it consists of arrows joining point and another arrow connecting the images through the morphism of Lie groupoids. Okay. The importance of the homotopy pullback, although in general its definition is not an easy thing at all, as you can see, is that it proves precisely that Morita equivalence is indeed an equivalence relation in the category of Lie groupoids. And through the homotopy pullbacks, through the notion of homotopy pullbacks, is at the very end what allows you to talk about equivalence relation from Morita equivalence, and then therefore to define differentiable stacks. So although technical, it's a very important definition. Okay, so now let me talk about Morita maps, right? This thing here about homotopy pullbacks is pretty well explained in an article by Matías del Hoyo, right? I will tell you at the very end the reference. Okay, fine. Morita maps. Okay, so Morita maps are a very concrete and special kind of morphisms of Lie groupoids, right? So let us consider a Lie groupoid morphism between two Lie groupoids, G and G prime, right? Of Lie groupoids. And we introduce the following two definitions. Well, first of all, we say that, well, the first one is like the morphism of Lie groupoids is fully faithful for the reader familiar with category theory. This has a very concrete sense, right? It's fully faithful if it induces a good pullback between the anchors. As you imagine, it's like if anchors appear, is our locally, well, if our Lie groupoid is transitive and so on, is a very nice construction. So, meaning that it induces a pullback between the anchors. Here we have like the anchor of G, which is X, S, and T, 2m times n. Here, of course, natural arrow is like the product of the maps between objects. And what we have here is like, this is the anchor of the another groupoid. And what I'm saying is like, this is a good pullback. Right? Okay. And the second definition is like, we say that this thing here is essentially surjective if this thing here is a surjective submersion, right? And remember that things here were like, let me write, this was like from X prime, this is an arrow in G prime, from the image of X, which is a fiber product. Okay, if this projection here, this map here, is a surjective submersion. Okay, and do you remember when we were talking about the very first definition of pullback of a Lie groupoid along a map? The condition I said that it was more natural was this thing, was precisely this thing here, right? to be an essentially surjective morphism of Lie groupoids somehow. So this condition here appears a lot. You know, like the composition of a projection with the target of one of the Lie groupoids, defined, of course, with the pullback along a map, is a surjective summation, right? Okay, and then we see precisely that a morphism of Lie groupoids, which is both fully faithful and essentially surjective, is a Morita map. And indeed, Morita maps, as we will see, are more natural than what one should think after seeing like the very first definition, right? So a morphism of Lie groupoids is a Morita map if it is fully faithful and essentially surjective. Both things, right? And in this case, one denotes Morita maps following Matías del Hoyo in this way, only between the sets of albums, right? And we can say that G, two Lie groupoids G and G prime, are Morita equivalent if there exists another Lie groupoid H such that we have like G prime here and G, and this third Lie groupoid H is equipped with Morita maps onto G and onto G prime, right? So two Lie groupoids are Morita equivalent if there exists another third Lie groupoid equipped with Morita maps onto the Lie groupoid G and the Lie groupoid G prime. Okay. So what we really want is to obtain a category in which Morita equivalence between Lie groupoids is an equivalence relation. If we take the category of Lie groupoids with objects, Lie groupoids, and maps, precisely morphism of Lie groupoids, Morita equivalence is not an equivalence relation there. So what we have to do is like to replace the morphisms in our category by another kind of things which are more close to the notion of Morita equivalence than arbitrary morphism of Lie groupoids. So it is somehow a categorical problem, right? Okay, but the important thing here about Morita equivalence is that maybe you have heard about this, is that suppose that we have like, well, and provided that R Morita equivalence, we denoted that G in this way, right? G is Morita equivalent to G prime. This is the standard notation, right? Suppose that we have like two Lie groupoids which are Morita equivalents. Well, what we have is that if G is Morita equivalent to G prime, we can take in a very natural way the associated orbit spaces, right? These things here, as you can imagine, in general, they are not manifolds at all, right? But they are topological spaces, okay? This question here is like saying it is the space of points which are joined by arrows of G, and the same with G prime is the orbit space of a group, right? Provided that the Lie groupoids are Morita equivalent, these things here are homeomorphic, right? So if we have like two very different spaces which are much singular, I mean, as topological spaces and so on, that they are orbit spaces, and we know that they are quotients of orbit spaces of Lie groupoids, which is indeed a very natural thing, because Lie groupoids, as we know, they are very useful and they appear a lot. one way to prove that they are non-homeomorphic, which is indeed a very difficult thing, as you know, if you have studied like algebra and topology, instead of using like that topological techniques, one can prove that the associated Lie groupoids are not Morita equivalents, which is sometimes much easier. Okay, so examples. Suppose that we have one Lie groupoid G, right, over a manifold M. This Lie groupoid is Morita equivalent to the trivial Lie groupoid, right, of a manifold N over N, if and only if G is a submersion groupoid and the Gaussian space is regular in the sense that it is precisely the manifold M, right? The orbit space. So a Lie groupoid is Morita equivalent to the trivial groupoid if and only if it is a submersion groupoid, which is a very concrete groupoid associated to a foliation, the one determined by the submersion, and the orbit space is precisely regular and it is a manifold, which, as you know, it does not occurs in a lot of cases. As for instance, the Kronecker foliation, right? Where the Gaussian space is not a manifold. So the other example is like, suppose that we have a Lie groupoid over a manifold M. This is Morita equivalence to a Lie group, right? Which is a Lie groupoid over a point. If and only if the Lie groupoid G is transitive and the isotropy group at a point X is isomorphic to the Lie group G for every X in M, right? And now, just let me, well, maybe this is it's just the last thing, but I think that this a very, very interesting thing to end with maybe Lie groupoids and talk about the algebroids in January is the notion of differentiable stacks, right? So in order to talk about differentiable stacks, what we have to do is what I was saying before is like to obtain a very precise notion of what morphisms we have to consider between Lie groupoids to for Morita equivalence being an equivalence relation there. And well, it's like some years ago they realized that the very good notion of that is not of Morita maps, but that of generalized maps. So Morita maps between Lie groupoids are a very special kind of the so-called generalized maps. And Morita maps are somehow invertible generalized maps, right? Well, so a generalized map between two Lie groupoids is like this philosophy of Morita maps. It's like using another Lie groupoid. It's a map which is defined in this way as a fraction, and you will see why right now. It's denoted in this way. It's from a Lie groupoid G, is denoted with this continuous line onto another Lie groupoid G prime. Is denoted in this way, but it consists precisely on another third Lie groupoid H. We have like the map psi here, and it's like the denominator, the invertible map psi, which is this notation of fraction, is precisely our phi, which is a Morita map. So a generalized map consists on two morphisms of Lie groupoids psi and phi, such that one of them is a Morita map, somehow, right? Okay, and this is onto G for sure. So a generalized map is something in this way. We say that two generalized maps are equal are equal if there exists another generalized map, which is, say 3, 5, 3. The one in the denominator is always the Morita map, right? Up to isomorphism of Lie groupoids, such that the following diagram commutes. So here we put x1, h1, which is prime. We have our Morita map here, which is like phi 1. Then we have our h2 here, psi 2 onto g prime, morphism of Lie groupoids. Our another Morita map here, which is phi 2 onto g. Well, sorry, I put g1 here. It's only g, right? And we say precisely that these two generalized maps are equal if they are connected by another generalized map. So here we have h3, g prime, another Morita map here, which is phi 3 onto g. Here we have equalities, and we have morphism of Lie groupoids, such that this diagram commutes. So we say that two generalized maps are equal if they are connected by another generalized map up to isomorphism. And precisely the set of generalized maps between two Lie groupoids is denoted in this way. This is the set of generalized maps, right? And the point is like this composition, generalized maps can be composed using homotopy pullbacks, right? So this is the main point. Okay. So now this is the set of generalized maps, right? Using here. So some examples. Whenever we have two manifolds and to M prime, the set of generalized maps is the set of smooth maps, so morphism in the category of manifolds from M to M prime, right? So the other example is when we have G and G prime Lie groups. The set of generalized maps between G and G prime is precisely morphisms of Lie groups between G and G prime up to inner automorphisms of G prime. And this is precisely something related to the, if you know, the cohomology of G with values on G prime. So this is why I guess that they use that notation, right? So the point here is like we can form a category dataset Lie groupoids with objects Lie groupoids. And arrows are just the morphisms between two Lie groupoids in this category are just generalized maps. And the point is like in this category, Morita equivalence is an equivalent relation, right? So the point is like the problem is like in the usual category of Lie groupoids, which just morphism of Lie groupoids, this with a set of morphisms, you have a problem with Morita equivalence. But note if you change like usual morphism by generalized maps. Well, so the last technical detail, right? Suppose that you have like this thing here. How to compose generalized maps, right? So suppose that you have like two generalized maps, which are psi. So this is from G to G prime, right? So this means that there exists a third Lie groupoid H with a Morita map 5 onto G, and then our map site onto G prime. Then we have another H prime, right? Suppose we have this is from G prime onto G prime prime. So we have Morita map here onto sorry, maybe this arrow has to be big. So this is a Morita map. Sorry. This is phi prime prime. This is psi prime. Wait a minute. Okay, in this way, right? So we have like two generalized maps from G to G prime, which means Morita map from H to G, and map psi from H to G prime, then Morita map from H prime to G prime, and then map from H prime to G prime prime. And the point is like we want to compose these ones, so we have to construct a generalized map which goes from G onto G prime prime. And what you do is like you take like this thing here, and the homotopy pullback over G prime. And this has a certain map here, which is a Morita map, and another map here, which is psi. So the point is like the composition is defined as, and for sure you have a Morita map from here to G, because composition of Morita maps, as you can expect, is a Morita map. And then this map here, right? Of course, you can construct like this thing here. Here you can put another Lie groupoid and another generalized map up to isomorphism. But the thing is like the clearest representative is like the homotopy pullback. So the necessity of homotopy pullback is like to prove that whenever we consider generalized maps, Morita equivalence is an equivalence relation. And for sure, I mean, I guess that it is also useful in another context. So far, I have not seen it. So what we have is like in this category of Lie groupoids with generalized maps, we can consider the quotient category up to this equivalence relation. And this is defined as the category of differentiable stacks. And precisely to a Lie groupoid G over M, it associates, well, the thing is like whenever we have a Lie groupoid G over M is differentiable stack is denoted by, sorry, it is like this thing. And the point is like, it contains the necessary differential information in order to study this orbit space here, which may be very, very, very singular. But differentiable stacks contain like differential information to treat this somehow, right? And if you're interested in this, you may check like a very recent paper on the archive by Well, there are a series of 2 papers. They are by Marius Krajnik, Rui Loja Fernandez, and David Martinez Torres. They are named Poisson manifolds of compact type, right? So they use a lot of these things and orbifolds and so on. And finally, just let me say, this is the last thing, sorry. There is that a generalized map is invertible if and only if this map here, 5 is Morita, right? So the generalized map is invertible if both maps are Morita. So finally, the thing is that 2 differentiable stacks are isomorphic if and only if the Lie groupoids are Morita equivalent, right? So isomorphism of differentiable stacks is isomorphism, Morita equivalence of Lie groupoids. And just finally, the references. The first one is Matías del Hoyo on Lie groupoids and differentiable stacks. I suggest you to check like this, the third version on archive from Weekly. The second reference is like from Enrique Burstein, Cabrera, and Matías del Hoyo again, which is like vector bundles over Lie groupoids. And algebroids, right? And this is like in advances in mathematics from 2016. And the third one, which is a very, very nice book I like a lot, is like from Nordic. And Marson. Which is Introduction to Foliations on Lie groupoids. So this is all. I hope you like it, and thank you for your attention.
Thank you, Oscar, for your very nice talk. So are there any comments or questions? Well, I'd like to ask you a general question of, well, this philosophy of Morita equivalence and so on. So it seems like the most general notion that one can develop of quotient, right? And in particular, a lot of the people that we are in the audience or among the organizers of this Reading Groupoid, we are interested in geometric mechanics where quotients usually represent like getting rid of the symmetries of some, let's say, redundant degrees of freedom of some dynamical system. So the idea is that you have some manifold that is the phase space of a mechanical system or your space-time or whatever, and you get rid of some symmetries. And of course, sometimes one imposes very restrictive conditions in order to don't get out of the initial category, which is what one does in Marsden-Weinstein reduction, for instance. And this seems going the opposite way, right? Like the minimum ingredients so that you can develop some sort of orbit space, of course, with the price of losing the structure of manifold and so on.
Yeah, so how to apply that to mechanics, right? I guess that.
Yeah. Like, well, of course, it's as you said, can be very singular space, but I guess you can have some sort of very like you have some dynamical
Yeah. I
system
know.
on some geometrical sense, let's say, and you get rid of the symmetries, and you end up with this differentiable stack, and somehow maybe you can study dynamics there and try to reconstruct it or something.
Yeah. So the point is like, well, at least for orbifolds, I have some ideas of how it should work because, as far as I know, on orbifolds you have like this. I know that symplectic structures on orbifolds, like Marsden-Weinstein reduction, well, but maybe with another different name, right, Bartosz? I mean, exists on orbifolds, and you can do a lot of things there. You have like also vector fields. You have whatever you want. So for the case of orbifolds, yeah, but for arbitrary differentiable stacks, I have no idea, and I have nothing seen about application of that to very mechanical problems. I know that there are some people working on those things, like on shifted structures and so on, but I have not seen yet an application of differentiable stack to mechanics.
I see.
And I am also, as you probably know, very interested in that.
Of course.
But I don't know.
I mean, in case also in reduction, I also don't know in case of differentiable stacks, but there is also a notion of diffeology.
Yeah, I know.
And yeah, so people do reduction in the diffeology setting.
Which is
I don't know about the mechanics, but in a symplectic, they consider symplectic diffeology and they trying to reduce the geometry.
Yeah, I know that for the case of diffeological spaces, there are examples in physics, right? Like using that. I think so. But for the case of differentiable stacks, well, maybe they are, but I don't know where. Maybe in these Poisson sigma models or some things like that.
Yeah, but still diffeologies are more general than orbifolds.
And then differentiable stacks?
I don't think so.
Okay.
So then another natural question, well, I guess it's complicated to answer, but would be what is the relationship between the diffeological spaces, differentiable stacks? Like, are diffeological spaces a subset of, okay.
I don't know that, but mainly because, well, the first time, like, somehow I understand like the most basic aspects of construction of differentiable stacks were the last 5 days. and now the idea is like, for me, it would be like, very interesting, like to, first of all, to understand like how these things work, but also with examples, like also like with very concrete things from mechanics and so on. And then like, it could be also for sure like very interesting to, like to look for the relation between diffeological spaces. For sure, it has been studied. I think so, but I don't know where. I mean, I can search after the talk and tell you if I find something.
Thank you.
Some more questions?
I mean, there is a website, diffeology.net, and there are publications about.
Yeah, there's this, I forgot his name, but this professor that gave lecture was in the theory of duality or in what
Patrick Iglesias.
Gamma,
Patrick Iglesias.
Yes, exactly.
Patrick Iglesias.
Exactly.
Yeah. He was a student of Suryo, I think, right?
This is a good place to start looking for the relationship, I think.
Yeah. In fact, I think in his seminar, someone asked essentially the same question, and his answer was basically like, of course, this is not any type of theory, but if I remember from that other seminar, he said something like, yeah, that people now were studying differentiable stack, but he was still with the theology because it was the topic of his thesis, and he was too old to switch topic. That's what he said.
Yeah,
something like that,
I mean,
if I recall.
I know that there are a lot of things there. They are also like diffeological groupoids, right? For instance,
yeah.
I have seen that, but don't know. Okay, guys, so regarding next semester, we start with Lie algebroids, right?
I think so, yeah.
Yes.
Well, that's nice also.
I don't think we have a speaker yet, no?
No, we have to commit someone.
Okay.
I mean, I can talk after I'm more free now.
Okay.
Mhm.
Me too. So.
By the way, can we
what-
stop the recording? I mean,
Yeah.
Sorry. Yes.
Yes, that's what I was going to ask.